Welcome to practical 2, which is on step bar with the thermal effect. So in this practical we are going to study the effect of thermal loading on the step bar. In last practical we have studied the effect of axial loading on the step bar. Now before going to the problem statement, let me tell you what is a thermal loading and what is the effect of thermal loading on the structure. So you might have undergone a science practical in your school where we have one ring and there is a copper ball, and that ball is able to move inside the ring, and when it is heated, that ball, then it is not able to cross out the ring. The reason is that copper ball is expanded due to thermal loading, right? So whenever we apply a thermal load or a temperature on any body, then the body might expand or contract, right? And that expansion or contraction can be given by this. That contraction or expansion can be given by alpha L T final minus T initial. T is temperature, final temperature minus initial temperature. So we can write down like this: alpha L delta T. And this you have gone through in your strength of material or material science classes, right? So where alpha is a coefficient of thermal expansion, every material has a specific coefficient of thermal expansion, which defines its behavior of how it's going to expand or contract. L is the length in a meter and delta T is a temperature difference. So if temperature deformation is permitted to occur freely, means we are allowing it to freely expand or contract, then there will be no stresses, right? Let's consider this pen is of metal. So consider that I'm heating at the one end, so it tries to elongate, right? If I'm not restricting it elongation, there will be no stress, right? If I'm freely allowed to move, then there will be no stress. But if I'm closed back in some room, then the stress will be generated. So similarly, if I'm restricting its expansion, then there will be stress generation due to the thermal loads. That internal stress is known as a thermal stress. For the homogeneous rod, which is shown in the image, between two rigid supports, the thermal stress can be computed using this formula, where stress sigma is equal to E alpha delta T, and this is the derivation you can go through, right? So stress will be E alpha delta T, and that we are going to also compute for this problem statement which we are going to undergo, and we are also going to compare it with the FEA result in ANSYS software. So in next video we are going to understand the problem statement, and then we'll start the ANSYS problem.